Hello everyone, myself Sravanthi, working as an assistant professor in the Department of Data Science and Cybersecurity in MLR Institute of Technology. Today our topic is bottom-up parser. So the overview of our topic is the definition of what bottom-up parser, the examples, and what is shift, what is reduce, and what is LR parser. So these are the topics which we are going to cover in today's topic. So initially, what is a bottom-up parser? So before that bottom-up parser, what is a parser? Parser is nothing but we can tell it as a syntax analyzer. So parser is nothing but it is a syntax analyzer. So the syntax analyzer, what it checks is it checks the syntax of the tokens. It checks the syntax of the tokens. If the syntax of the tokens are correct, it generates parse tree. It generates parse tree if it is correct. If the tokens are wrong, if the syntax of the tokens are wrong, it generates error. So this is nothing but a parser. Parser is nothing but it generates a syntax. It is nothing but a syntax analyzer. It generates syntax of tokens. It checks the syntax of the tokens are correct. If the syntax of the tokens are correct, it generates parse tree. If it is wrong, it generates error. So coming to this, there are two types of parsers are available. The first one, parsers are of two types. So first one is top-down parser and the next one is bottom-up parser. Bottom-up parser. So in that we are going for the bottom-up parser. Our topic is bottom-up parser. So what is bottom-up parser? Here bottom-up parser is nothing but we are going to generate the tree from bottom to top. We are going to generate the tree is nothing but bottom to top. Bottom to top is nothing but, so initially we will generate a parse tree like top to down. We will generate a parse tree top to down. Nothing but we are going to have a root node. That root node is given as an input and we are going to generate a sentence. We are going to generate sentence or nothing but input string we are going to generate. We are taking the root node and we are going to generate the syntax sentence or a string. But coming to the bottom-up parser, we are going to take the input as a sentence. We are going to take the input as a sentence and we are going to generate the root node. Root node is nothing but the start node. We are going to generate root node or start node. Sentence is nothing but we are going to take a leaf node. We are going to take leaf node. So that is nothing but we are going to call it as a bottom-up parser. So initially we will generate a parse tree by taking the root node and we are going to generate it in a sentence. Nothing but string we are going to generate. So this is nothing but top-down parser. So now in this bottom-up parser, what we are going to do is we are going to take this sentence as an input and we are going to generate a root node. Nothing but in a reverse direction. So that is why we are going to call it as a bottom-up parser. That is why we are going to call it as bottom-up parser. See here, bottom-up parser starts from the leaf nodes of a tree and works in upward direction. Till it reaches the root node. Until it reaches the root node, it generates the productions. So it takes the input as a leaf node. Leaf node is nothing but it takes some sentences. Some sentence as the input it takes and it generates the productions until it reaches the root node. So that is nothing but we are going to call it as a bottom-up parser. Same here. Here if we start from a sentence and then apply production rules in reverse manner in order to reach the start symbol. In reverse manner. Actually in the bottom-up top-down parsing, root to the sentence we are going to generate. So this one we are doing it in a reverse order. So that is nothing but sentence we are taking and we are going to generate the root. So that is we are going to tell it as we are going to apply it in the reverse order, reverse manner in order to reach the start symbol. So bottom-up parsing is also known as, we are also going to call bottom-up parsing as shift-reduce parsing. We are going to call it as shift-reduce parsing. It is used to construct the parse trees for an input string. Initially, I told you that parser is nothing but it generates a syntax analyzer. It is nothing but syntax analyzer. It consists of tokens. By using these tokens, we are going to generate the parse tree. Same way, it is used to construct a parse tree. The name itself tells us that to generate a parse tree for the given input string. In the bottom-up parsing, the parsing starts with input symbol and constructs the parse tree up to the start symbol by tracing out the rightmost derivations. So the rightmost derivations of a string in reverse order. So we are going to generate the string in reverse order by taking it as a rightmost derivations. So here what we are going to do is we are going to take the input symbol, nothing but the set of state. We are going to take an input string or sentence as an input, and we are going to derive it, and it is going to generate the start symbol. If we trace it out, we are going to get a rightmost derivation. If we are going to trace it out in reverse manner, we are going to apply a rightmost derivation. We'll see in detail with an example for this bottom-up parser. So, see here diagram, bottom-up parser is nothing but we are going to have a shift-reduce parser. This shift-reduce parser is nothing but LR parsing. And this LR parsing is divided into SLR parsing, LR parser, LALR parser. So, these are the different types of parsers. So, we are going to discuss what is shift-reduce parser, what is LR parsing, and what is SLR, what is LR parser, and what is LALR parser. So, coming to the example for the bottom-up parser. So, these are the, it is a grammar. A grammar consists of productions. So, this is the input string which is given. Now, for these input string, we are going to apply the bottom-up parser. So, how we are going to apply? ID into ID is my string. Or nothing but we can call it as sentence or string or leaf nodes. Sentence or string or leaf node. Okay, leaf node. Leaf nodes consists of the terminals. Sentence consists of terminals. Okay, so what we are going to do? Now we are going to apply the productions. See here, ID is there. We are going to check each string, each alphabet, whether it is matching with the productions or not. So, the handle, nothing but ID, is going to be checked with the given production, whether it can be handled in the rightmost derivation. If it is handled, now we are going to reduce it. So, now ID, check it in the productions. Yes, ID is found in the rightmost derivation of the productions, and that can be replaced with F. ID is replaced with F. So, not F, it is replaced. Now, check it, F. Still, F can be reduced. No, it cannot be reduced. So, now, next, what we are going to have? F. F can be reduced. See here. F can be also reduced to T. T star F. F can be reduced. So, it can be reduced to T. The next. So, till T can be reduced. Yes, it can be reduced to E. But if I reduce these T to E, I cannot find. For example, if I reduce T to E, next we'll check it, star ID. IDs can be reduced to F. So, E star F, any production is available. There is no production with this E star F. So, I'm not going to reduce these with E star F. So, that is why I'm stopping it with only till T. If I reduce this T to E, I cannot find the productions of E star F in my given grammar. So, that is the reason I'm not going to reduce. Once we are going to handle the productions, we need to check whether that particular production is available in our grammar. If it is available, then only we can derive it. So, by using this, we can, by these productions, we can check whether it is reaching the start symbol properly or not. So, the next, star is as usual. So, the next what I have here, ID is there. Now, ID, check ID. It can be reduced to the EF. So, the next F is nothing but I am going to keep it as it is. So, T star F. Again, I am writing T star F. So, T star F. Check it. T star F, whether it is available in our production. You check this T star F is handled in the right side of the production. Yes, it is found in the right side of the production. It can be replaced it with T. Now, check this T is found in the rightmost derivations of a terminal. Yes, T is found. It can be replaced it with E. So, the given sentence, when I am going to derive it, nothing but when I am going to derive by replacing the strings with the given productions, I am going to reach the start symbol. The start symbol of my grammar is E. I reached the start symbol. So, this is nothing but bottom-up parser. We are going to have a string. That string I am going to derive until I reach my start symbol. So, what we have discussed here, In the bottom-up parser, the parsing starts with the input symbol and construct the parse tree up to the start symbol by tracing out rightmost derivations. See here, by tracing out rightmost derivations, in reverse manner is the condition we have written. We can also tell like E tends to T can be replaced with T star F, T can be replaced with T star F. Then after what I am going to do, F is replaced, F tends to ID, next T tends to ID. See here, ID star ID. So what I am going to do, if I take this bottom-up parser in reverse manner and I am going to apply the rightmost derivation over here. Rightmost derivation over here. See here, first E is taken, E is derived to T, E is derived to T. Then next T is derived to T star F, T is derived to T star F. After T star F, I am going to derive this ID. I am going to derive this ID. F tends to ID. Then next, afterwards, after completing the right part, I am moving to the left hand side and I am going to derive ID. So that is nothing but if I apply this bottom up parser in reverse manner, I am going to apply the rightmost derivation. We are going to apply the rightmost derivation. So this is nothing but the bottom up parser. Here, if I replace this T with E star F, production is not available. So that is the reason we didn't derive this one. We didn't derive this one. Okay. So check the same steps. First step is we are going to take the sentence. Then after I am going to replace the ID. ID is replaced with F. ID is replaced with F. And the next F is replaced to T. And next T star ID. It is replaced. So how this is written is, see here, we are going to write as it is a bottom up parser. Here I am going to show, here first I have written ID into ID at the top and I am going to derive until I reach start symbol. But here I have written in reverse format. Nothing but this is the procedure I have written here. So first we write like this, then we can find it like this also. Both are pointing to same. So the next classification of bottom up parsing. The bottom up parsing is classified. It is, we are going to derive it into shift reduce parsing. The shift reduce parsing consists of operator precedence parser, LR parsers. LR parser consists of SLR, CLR, LALR parsers. And also one more parser is there, LR of 0 parser. So these are the 4 parsers we have and the other one is operator precedence parser. So all these parsers we are going to discuss. Next, so what is shift reduce parsing? So to construct a parse tree using shift reduce, we have 2 techniques are there, 2 unique steps we need to follow. The first one is we need to shift and the next one is reduce. These are the 2 things we need to follow when we are going to apply shift reduce parser. So shift is nothing but moves the current position to the right in the input stream by shifting the next input symbol onto the stack. For example, I have a string ID into ID. ID into ID. So this is nothing but my input string and I am going to have one stack. So first I need to do is I need to shift the from left hand side. I need to shift this ID to the stack. Where I am going to shift ID to the stack? At the top of the stack we are going to shift. Initially the stack consists of $, as the stack is empty. Then after I am going to shift this ID to the top of the stack. So that is nothing but directly it won't move. So we are going to apply the operations as shift. Nothing but when I apply shift is nothing but from the input stream, one input is moved onto the stack. One input is moved onto the stack. The same moves the parser's current position to the right in the input stream by shifting the next input symbol onto the stack. Now the cursor is as it is at the start symbol. The stack it is moved. The next it moves the cursor here. Again it moves onto the stack. If it is not reduced, the shifted symbol is treated as a single node of the parse tree. Now ID is shifted onto the stack. This ID is treated as a single node for the parse tree. Yes, when I am going to construct a parse tree, each string, each symbol we are going to treat it as a node, single node. Next, so the reduce. What reduce it does is when the parser finds the complete grammar rule and replace it to LHS, it is known as reduce step. See here, I have shifted shift ID. ID is shifted onto the stack. ID is shifted onto the stack. Nothing but in my stack, this is the position it will be, $ID. Now what is the reduce is? So the reduce, what it does is, the reduce step checks whether this ID is present in my grammar in the rightmost derivation, in the rightmost part of my grammar. So grammar consists of productions. In the productions, the ID, nothing but the part which, the symbol which is shifted onto the stack, whether these is present in the RHS part of the terminals, RHS part of the production. If suppose it is found here, F tends to ID. For example, this is my grammar consisting of F tends to ID. If this ID is found in my grammar in the right hand side, then replace this ID with the left hand side non-terminal. Replace it with left hand side non-terminal. So nothing but we can write it as reduce F tends to ID. Ref tends to ID. This ID is replaced with F, $F. $F is the step it is replaced. See here, when the parser finds a complete grammar rule and replaces it to LHS, it is nothing but we are going to call it as reduce step. This occurs when the top of the stack contains handle. Nothing but we are going to call, this is nothing but each element or each symbol we are going to call it as handle. When substring is found in the input string, whether that is matching to the RHS of the production or not. If that it is matching in the RHS of the production, then replace it with the terminal, non-terminal which is found in the LHS part. If it is not present, then shift the next input symbol onto the stack. If the ID is not present in the RHS part of my productions, then shift next symbol onto the stack. Initially ID is shifted. The next what I am having star. So star, F star, whether it is found in my RHS production, not there. So the next ID, shift ID, F tends to I, F cross ID. So nothing but checks. F cross ID is present? No. The next ID is replaced, reduce ID. So that is the procedure we are going to follow for the shift reduce parsing. So there are the two unique steps that should be followed to construct a shift reduce parser. The first one is shift and the next one is reduce. Shift is nothing but it shifts one symbol at a time onto the stack. So further, to shift one symbol we are going to use shift step. To reduce is nothing but if that symbol is found in my grammar, then we are going to replace it with reduce step. Nothing but we are going to reduce that production. So that is nothing but shift reduce parsing. Example. So we will see in detail of this. So this is my grammar. A grammar consisting of productions, E tends to E plus E. So these are the productions I am going to have. This is the input string. This is the input string. So here I am going to take the input string and stack. Stack holds the symbols on it. And action. Action is nothing but there are two types of actions which we have discussed. The first one is shift and the next one is reduce. Shift and reduce. These are the two actions we have discussed just now. So first, initially the stack is empty. So we are going to place the stack it with $. We are going to place the stack initially with $, as it is empty. And the input string should end with $. Input string should end with $. So this is the input string I have copied here and it is ending with $. So what is the first symbol present in my input? ID1. So shift. What type of action I am going to do? Shift. So it is shifting onto the stack. So $. And it is, I am going to have ID1. Now, what is the remaining elements present in my input? Plus ID2 into ID3 $. So check whether ID is present in my grammar. Yes, in the grammar, in the right hand side of the part. So ID, it is present. So what it is? It can be replaced it with E. So what I am going to do? ID1 is reduced to E. So nothing but what type of action? Reduce action we are going to do. Reduce by E tends to ID. So now ID1 is reduced to E. ID1 is reduced to E. So the next what I am having in the input, the symbol is plus, E plus. Anything is there in my production? Nothing is there. So the next, shift ID2. ID2 is shifted. ID2 is shifted here. ID2. Check E plus ID2. Anything is there? No. So I need to replace this ID2. ID1, ID2, ID3 doesn't matter. ID. It points to same. Okay. For to show the differences for you, I am placing it with ID1, ID2 and ID3. So ID2. Check. It is there? Yes, ID. So reduce it by E plus E tends to ID. So it is replaced. E plus E is there. Check E plus E is present or not. Yes, it is present. So replace it with E. Replace it with E. E plus E. So I'm having E plus E. I can reduce. But what I'm having is, we are going to first move the steps. That way is also correct. Here E plus E is there. I can reduce it to E plus E. So before that, just I'm showing the procedure to what is shift and what is reduce. The next what I'm having star. So star is moved here. The next what I'm having ID3. ID3 is nothing but shift ID3 is moved here. Shift ID3 is moved here. So the next one what I'm going to do, reduce. We are going to reduce it with E tends to ID. So it is reduced. E tends to ID. E star E. So now E star E is present in my grammar. Yes, it is present in my grammar. So reduce by E tends to E star E. So it is reduced to E plus E. Check whether it is present. E plus E. Yes, it is present. Reduce. So nothing but I'm going to get $E. E is nothing but my start symbol. So these are nothing but all the bottom up passes. I'm going to take the input string and I'm going to generate until I reach my start symbol. See here, E plus E is there. These also, it also gives me the same result. See here, $E plus E. I can reduce? Yes, we can reduce. Both are giving me the same output. Here in this grammar which I have taken, directly I inputted all and then I reduced. If you want to reduce here, you can reduce E plus E. E, it is giving me E. The next what I have, star. So what it is taking, ID3. And the next what it is going, E star E. Next, $E star E is present. Yes, it is present. So what it generates? See, both is giving me the same output. Nothing but start symbol it is generating. So it should generate the start symbol and the input reading should also complete. Nothing but it consists of $. Dollar indicates that I have completed reading my input string. So this is of the shift reduce parsing. One example. In detail we will discuss in the next coming class. LR parser. So the next LR parser. So it is nothing but it is a non-recursive parser. Here it is a shift reduce. It is a bottom up parser. Yes, LR parser is nothing but it is a non-recursive parser. It is shift reduce. We are going to apply shift reduce and the next we are going to have it is a bottom up parser. These all comes under bottom up parser. It uses a wide class of context free grammars. Here we are going to use the context free grammars which makes it most efficient in the syntax analysis technique. So here LR parser is also known as, we are also going to call it as LR of K parser, where the first L stands for left to right scanning. We are going to scan the given grammar from left to right, and R is nothing but the rightmost derivation. We are going to apply rightmost derivation in reverse manner, and K is nothing but look ahead symbol. K is nothing but look ahead symbols. Suppose I am having LR of 0 is nothing but 0 look ahead symbols. If I have 1 LR of 1 parser, LR of 1 is nothing but 1 look ahead. It is nothing but 1 look ahead. It is nothing. So K can be anything. K is nothing but K denotes the number of look aheads to make the decisions. So this is nothing but about LR parser. Okay. Thank you.